Hi everyone, and welcome to yet another virtual chemistry lesson in thermochemistry aimed at the Swedish Chemistry 1 course. In this video, I will introduce the concept of entropy and how entropy is related to spontaneous reactions and Gibbs free energy. The picture shows a firework display where we definitely have an increase in entropy. You'll probably be able to explain why at the end of this video. So, something that we have seen is that some endothermic reactions can occur naturally. But how come? Really, why can they do this? Well, we've learned that endothermic reactions can occur spontaneously. For example, the reaction between barium hydroxide and ammonium chloride that you see down here. This is a reaction where you mix two solid compounds together. Gas, liquid, and an aqueous solution is then formed, and the temperature drops from room temperature to about -20 degrees Celsius. Since energy has to be drawn from the surroundings into the system, surroundings are cooled down, this must be an endothermic reaction. But why does this happen naturally? Endothermic reactions, they result in the formation of more energy-rich bonds. So how can more energy-rich bonds be formed in a natural spontaneous process? We've talked about that the less energy-rich the bonds are, the more stable they are. So something is very strange here. So let's see if we can understand what's actually going on. So why can more energy-rich bonds be formed spontaneously? We need the concept of entropy to answer this question. So, entropy is a measure of the degree of disorder. So what does this actually mean? Well, let's start by thinking about the states of matter. For solid compounds, the particles are packed tightly in various types of, for example, crystal formations. They're ordered in a pattern that repeats all over again, over and over and over again, in various types of structures like this. When you have a liquid, then you have particles moving about, they're switching places, but they still bond to each other and stay together. And when we have gas, we will have particles all over the place, little intermolecular bonding will occur, and these particles will fly away from each other and expand to fill any space that the gas is occupying. If we think about order in relation to this, we can deduce that a packed, organized structure like this is more ordered than a structure that moves about, particles switch places. But this is more ordered than the gas, because in the gas, the particles are all over the place, they don't bond. Here at least they stay together. So solid will have a higher degree of order than a liquid, which will have a higher degree of order than a gas in turn. So how organized you are, you can think. And when it comes to entropy then, which is the degree of disorder, the gas will correspond to the highest degree of disorder. A liquid is more disordered than a solid in turn. So if we were to write the degree of disorder, the arrow would be the other way here. So it's a measure of how spread out particles within a system are. So degree of disorder. The symbol for entropy in thermodynamics and thermochemistry is the big S, and the unit is joules per Kelvin per mole. And I'm gonna show you this for a few more seconds so you can write this down. These are important notes to write down. And you can pause the video at any time you like to make sure to take those notes you find to be relevant for your studies. All right. In simplified terms, the second law of thermodynamics states that the universe strives towards an increased amount of disorder. Therefore, the universe strives towards an increased amount of entropy. And if you think about this, think about your own bedroom. Does it spontaneously on its own strive towards order or disorder? If you're like most people I know, your bedroom will eventually be quite disordered. There will be things scattered about in there, and you will have to put energy in to organize it and force it to go back to order. But naturally, spontaneously, it strives towards disorder. When the entropy of a system has increased, we write a positive value of delta S. So the change in entropy is positive. Then the entropy of the system has increased, which corresponds to less order. When the change in entropy is negative, then the entropy of the system has decreased and we have a higher degree of order, more organized, we can think. All right, so let's go back to our sample endothermic reaction here. In this reaction, we have two solid compounds being mixed, and they will react to form a gas, a liquid, and an aqueous solution. Here, we go from a very ordered state that is solid compounds to a state that is less ordered, where we have a gas, a liquid, and an aqueous solution. So going from a more ordered state to a less ordered state corresponds to an increase in entropy, and the delta S for this reaction will be positive. So that's how you can sort of predict how many reactions entropy will change. Look at the states of matter before and afterwards. If we start with liquids before and end up with gases, that will also result in an increase in entropy, for example. However, if we were to combine gases and the product is solid, then that would be a decrease in entropy. So the change in entropy affects if a reaction is spontaneous or not. However, we've also talked about that the change in enthalpy sort of affects if more stable chemical bonds are formed. And in nature strives towards a low enthalpy. We want more stable chemical bonds. So systems want to have a low enthalpy level, but we also strive towards a high entropy. So we need to factor in both the change in enthalpy and the change in entropy when we try to determine whether or not a reaction is spontaneous. There's a way to calculate this, and it's called Gibbs free energy. Gibbs free energy is calculated like this. Delta G, so the change in Gibbs free energy, equals the change in enthalpy minus the product of temperature and change in entropy. And here's the trick. This value for G, the Gibbs free energy, it's pretty much used just to see, is that value negative, is that value positive? If that value is negative, then we will have a spontaneous reaction. So whenever the enthalpy, temperature, and entropy are factored together this way, and the result is a negative value, then we will have a spontaneous reaction. The unit for Gibbs free energy, well, it's energy, so the unit will be given in joules like this. T, that's temperature, and whenever we're working in science, we usually talk about the Kelvin scale. So in this case, the temperature is given in number of Kelvin. And delta S, that is the change in entropy. And the unit for this is joules per Kelvin per mole. Delta H, that's the change in enthalpy, and the unit for that is quite often kilojoules per mole. Whenever we want to factor these together, we need to make sure that these two, joules and kilojoules, are matched up so that we either express both of these as kilojoules or as joules, so they match up nicely in our calculations. So that's a tip. All right. So Gibbs free energy, it's dependent on enthalpy change, entropy change, and the temperature that the reaction occurs at, expressed in number of kelvins. Sometimes we will have endothermic reactions occurring spontaneously if the change in entropy is high enough. So if you try to put in different values in the chemical formula that we in the formula, the mathematical formula I presented in the previous page. So if you put in different values of delta H, T, and delta S here, and experiment around a little bit, you will figure out a few general trends. These trends will be shown to you on this slide over here. So what this pretty much tells us is that if we have an endothermic process, an endothermic reaction, and the entropy of the system increases, then at high enough temperatures we will have a spontaneous reaction. So in this specific case, when we have more energy-rich bonds being formed, but the entropy increases, then we need to look at the temperature. And if we have high enough temperatures, the delta G will be negative. And that's because this expression here will be a negative value, and this will be a positive value. Right. Over here, we see that if we have an endothermic process, and we have, actually, hold on. Okay, there we go. So if we have an endothermic process and the entropy of the system decreases, this will never yield a spontaneous reaction, because the universe strives towards an increase in entropy and exothermic reactions, we can say. If these are both the opposite of that, and if we have both of these cases, then this will never yield a spontaneous reaction. Okay, if we have a exothermic reaction and the entropy increases, nature strives towards having low energy chemical bonds, so that corresponds to exothermic processes, and nature strives towards an increase in entropy, then this will always yield a spontaneous reaction. If we have an exothermic reaction but a decrease in entropy, then if we have low enough temperatures, we will have a spontaneous process. Okay. So, how do we use this? Well, we can use this to predict if reactions are spontaneous or not. Let's, for example, look at this following formula here, this following reaction. Is this reaction spontaneous at room temperature, 20 degrees? For simplicity's sake, we'll assume 1 mole of each substance. We know that the enthalpy change associated with this reaction is minus 95.4 kilojoules per mole. And we know that the entropy change of this reaction is minus 89.3 joules per mole per Kelvin. Okay. So, what we can do then is that we know that the temperature is 20 degrees. We convert that to Kelvin. So we're not at degrees Celsius, but we change that to degrees of Kelvin by adding 273.15. Then we can put everything into the formula. And what I've done here is that I've multiplied this value with 1,000 to get it in joules per mole instead of kilojoules per mole, because the entropy is also given in joules per mole here. Since the moles are 1, so this is this divided by 1, so then we have the energy there. This is divided by number of moles, so we have that as well, only 1 mole. So then we can simply put in the values. This is the value of the change in enthalpy expressed in joules per mole, minus then the temperature multiplied with the entropy change, which is negative. Then we will get a value of minus 69,221.71 joules, which can be written as minus 69.22 kilojoules. Note that the change in delta G is negative. That means that this is a spontaneous reaction. All right, so let's look at the same reaction but ask ourselves, at which temperature does this reaction stop being spontaneous? And we'll assume 1 mole of each substance as well. Well, we have the same parameters here, but at which temperature does this reaction stop being spontaneous? Well, you know that when delta G is negative, we have spontaneous reactions, and when it's positive, we have non-spontaneous reactions. Well, the temperature then where delta G is 0, that will be the temperature where the reaction will change from being spontaneous to non-spontaneous. So let's write everything into this reaction, and we write that delta G equals 0, and then we write temperature as an unknown factor like this. Then we can rewrite this expression like this, just writing this as minus 89.3x. That means that this value equals that value, because this value minus that is 0, so they will have to be the same. We can just change the signs so we have positive values, and then we calculate what x is. And that will correspond to then, at 1068.31 Kelvin, we will have the reaction will stop being spontaneous. That is the breaking point between spontaneous and non-spontaneous reactions. And that corresponds to a very high temperature. So above this temperature, the process will stop being spontaneous. All right. So that's a few examples of how you can use entropy and enthalpy changes and temperatures to predict whether or not chemical reactions will be spontaneous. I hope you've learned something today, and I will see you in a future video. Thank you very much for your help and attention.